Hi guys, good evening everyone. Welcome to this session, evening session on Unacademy for this CL Wadhwa backside bit solutions. Okay, so we will see what are these solutions for the question number 271 to 280. Actually, there was a session yesterday, but it is cancelled. Okay, I'll be discussing those questions in tomorrow's lesson. Okay, I'll be giving you all the questions from 261 to 270. I'll give them on this session then in the tomorrow's class. Okay, so today we shall discuss about these questions. Okay, so 271 to 280 is what we'll be seeing. Let's look at the first question, 271st question. The voltage across the various discs of a string of suspension insulators having identical disc is basically different due to dash. Okay, see, the question is, they are saying why is the voltage across the string of insulators disc we have. Okay, so we have a list of string of insulators, right? So all this insulator disc, now voltage across this each disc is basically different. Okay, we have something like this. Okay, now the voltages are not same, they are in this manner, right? We have already seen in that. Now why is that voltage differences are there across each capacitors? Each capacitors are of same material, they are of having in the same string itself, right? But the thing is, they are placed in different positions with respect to the pole, okay, with respect to the tower, right? Now these capacitors are located at different positions with respect to the tower of where the insulators are hanging. Okay, so each position, so this is you have a capacitor over here, and you have a chain, you have a link over here, right? So it's a basically iron link over here. Now that metallic link is basically making a ground capacitance. Okay, it's making a capacitance effect, it is making exhibiting a capacitance effect with respect to the tower. Okay, now that because of that shunt capacitance, it is shunt, right? It's ground, it's completely ground, tower is connected to ground. Now because of this shunt capacitance to the ground, I can say there are different voltages, differences in the voltages right now, because we have different currents flowing into the ground at different points of time, right? So you can at points of locations of the metallic links, right? So we have differences in voltages, you can say, because of the capacitors, and also because of these shunt capacitance with a tower over here. Tower is nothing but ground. So shunt capacitances to the ground are making the voltage differences here, right? So therefore option C must be the correct answer. Okay, so option C is the correct answer for 271st question. Now let's look at the 272nd question. What is this question given here? It is said that compared with a solid conductor of the same radius, corona appears on a stranded conductor at a lower voltage because stranding offers dash. So what is this stranding doing? What is the effect of the stranding on the corona losses? See, in a solid conductor, something like this, look at my effective radius. This is the center of the solid conductor, let's say that. Now this is the radius, let's say that we'll call this as radius, or this as the radius, or this as radius. Now the effective radius will be there, it is higher, you can say that the magnitude of the effective radius is higher. Whereas if you compare, if you look at the we have a standard conductors here. Now this is radius, and basically this is again radius, and it's all radius like this, right? These are all radius, and effective radius is not that higher. Okay, now look at the corona behavior with respect to the radius. We have seen that if you are having higher radius, I can say I will be having a lesser corona, right? Now we have observed that functioning, right? Now that we have seen that relation, now the differences in these radius is what affecting the corona, I can say clearly, that too at the lower voltages. But see, not only that thing is happening, but also look at the behavior of the conductor positions. See, this is one conductor, this is another conductor, like that we have a different number of conductors. Now this is the axis of the conductor. I would be saying that, let me change my color. This is the axis, and let's say I would be having the axis of the conductor. Main conductor is something like this, right? It is projecting along the line into the conductor. This is the axis of the line, right? Now what is happening, let's take conductor number 1. Okay, I will be taking that with a blue line. This is the conductor number 1. Now look what is happening here. This blue line is basically, it is projecting, it is creating a plane, right? It is producing a oblique section to a plane perpendicular to axis of the conductor. That means it is producing some oblique sections to the plane perpendicular to axis of the conductor. See, the plane perpendicular to axis of the conductor means, I would be saying the cross sectional area is a plane perpendicular to the axis of the conductor, right? So let's say there is a screen something like this. Okay, let me change the color of the pen. Now let's say this is a plane perpendicular to this yellow axis. Okay, now look at what this blue line is doing. So this blue conductor, the conductor number 1, what is it doing? It is providing some oblique section. It is a slant section. Oblique means this blue line is not in parallel with this plane. It is not even perpendicular to this plane. It is at something 45 degrees. Like that means, if you take, this is the plane of cross section area of the conductor. Now this is the axis of the conductor and it is perpendicular to the plane. Okay, now this blue line, which is the conductor axis, conductor number 1 axis, is something like this. It is not even perpendicular, it is not even in parallel, it is something like this, right? Now because of this, it is introducing some a oblique section. It is oblique section like that. Oblique means slant, right? So it is producing some oblique section to a plane perpendicular to the axis of the conductor. Yes, it is true. Because of that itself, we are having a higher corona in the case of a stranded here. We are reducing the effective plane over radius over here. Okay, so therefore option C is the correct answer. Let's look at the next question, 273rd question. The bus admittance matrix of the network shown in the given figure. Okay, now here they are giving us the values of per unit impedance. Okay, so they are giving the Z value and they are asking us to find out the bus admittance matrix, right? What is bus admittance matrix? We have Y is nothing but Y11, Y12, Y21, Y22. We know how to write these things, right? We have already seen that. Now here Z, it is Z means inverse of that is basically Y, right? Y is nothing but 1 by Z, which is nothing but 10. Now this is basically this Z value. That means I will write this as Z10 or Z01, something like that, or Y01 or Y10, and this is Y12, right, which is 1 by 0.2 is nothing but 5, right? So it is going to be 5. And you have what else do you have? I'll just put it over here. Y11 is nothing but, what is Y11, guys? Y11 is nothing but all the admittances connected to the bus number 1, 10 plus 5, right? 10 plus 5. Y12 means 1 to 2. What is the admittance we have? We have 5. Okay, 5 of that, and have minus over here, minus. But similarly, Y21 means between 2 and 1. 2 means all the admittance connected to bus number 2, which is nothing but only 5, right? So therefore only 5, which is option number D. Okay, option D is the correct answer. Let's look at 274th question. Now in this case we have different options. We need to choose the correct one. See, for the load bus, which of the following is correct, and for the generator bus, which of the following parameters are specified. Okay, see, for any bus in power system, first of all, if you are talking about bus number 1, bus number 2, like that in a given network. Okay, so if you are talking like in such a way, first of all, we need, by looking at certain parameters, we need to judge whether this is a load bus or generator bus. Okay, we need to specify that, we need to understand that, study that. So to understand that, every bus, so we have, let's say, two buses here. Now each bus, this bus will have four parameters, right? And this bus will also have four parameters. But the thing is, only two parameters are known, only two are known. Okay, and we need to find other two, right? We need to find other two. How are we finding that? By using the load flow analysis, right? Now, so for any bus, we should have two parameters. Suppose we generally have at load bus, what are the two parameters we can have readily available? Generally we can measure, means one is real power and another one is reactive power, right? So we can we can get these values from the load side, receiving end side. But from sending end, that's a generating bus, means what are the things I can have I can take already specified. You can say that, real power, I can specify that this much of real power is what I have sent right now, delivered right now, we can say generated right now. And apart from that, the magnitude of the voltage I can control from the generator bus only, right? From the generator, right? From the excitation part, I am controlling the voltage, and that means there is a generator connected to that bus. So I can say I can have a specified value. This is a known value. Magnitude of the voltage is a known value, right? So P, Q, V, and we even have the we even have the phase angle of the voltage as well. So phase angle of the voltage, we will be knowing that using slack bus. Okay, so slack bus or reference bus, we can find that as a specified quantity, which is reference. Generally it is taken as a reference value. Okay, so we will know that in slack bus. So look at these things what we have just derived right now. Load bus means real power and reactive power, right? So load bus means real power and reactive power, so option B is true. And generator bus is P and magnitude of the voltage, real power and magnitude of the voltage. And slack bus means magnitude of the voltage and as well as the phase angle of the voltage. We will be taking that as reference. Basically it is also sometimes called as reference bus. Okay, so option B is the correct answer. So let's look at the next question, 275th question. A Buchholz relay is used for a dash. So why do we use Buchholz relay? We use it in transformers, right? Exactly, we use it in transformers. But why do we use them exactly? See, this Buchholz relay is completely used against protection of faults. But what faults? External faults or internal faults is the question, right? So we need to understand this relay is completely functioned based upon the levels of oil inside the tank, transformer tank, you can say, right? So it depends upon completely level of oil. It doesn't even depend upon external parameters or external faults happening, right? So completely it is depending upon the internal faults only. It is not at all depending upon the external faults, right? So therefore option A is the correct answer. Protection of against the all internal faults will lead to change in my levels of the oil tanks, right? Oil tank level, right? Oil in the oil level in the tank. So that is the answer. Option A is the correct answer. Let's look at the 276th question. The line trap unit employed in carrier current relaying scheme is offering high impedance or low impedance. We need to find out. And if it is offering high impedance, for which signals is it offering, and if it is offering low impedance, for which signals it is offering low impedance, we need to see here. See, the concept in current relaying is carrier current relaying scheme. First of all, we will send the signals from the transmitter, right? So the transmitter will send the signals using these oscillators, and he will send that from here with some frequency, right? So here we'll have coupling frequency. Generally, why do we use these transmitters? Why are we sending the carrier signals? Means, see, we are using carrier signals just for the protection, okay, from uh, based from the relay scheme, based upon the relay schemes, and based upon the signals we are getting from the relays, we will communicate with the circuit breakers and other protection schemes, okay. So to communicate that, we need a control wire from substation, okay, from substation to the location of the relays, or somewhere other substations or somewhere like that, okay. Now we are sending the signals from these relays, okay, so from these relay points, and basically I want to send that signal to the relay point over here, okay, circuit breaker operating point. Now tripping point, I will call that as tripping point. Now it is not a small distance. For small distance I'll be using pilot wire, right? For small distances means, for small distances I can use pilot wire carrier protection scheme, right? Pilot wire protection scheme, I can use that for small distance. But for longer distances, for like 100 kilometers or something, not even 150 kilometers or something like that, it is not beneficial at all. So what we will do is, we will use the power lines only. So these are all power lines, right? So all these R, Y, B phases, different three phases, we will use that power lines only to carry the see another frequency signals also for the circuit breaker operating point over there, another point, okay, where the tripping point is should be happening, okay. How do we do that? Means we will be sending that signals using a coupling filter over here. So it's a series connected RC network over here, coupling capacitors. Now these coupling capacitors will offer low impedance to carrier frequency. Now carrier frequency means the carrier signal's frequency. It will offer low impedance. It will allow that signal to get into the line and reach that tripping signal point, okay. Now these are basically tuned to the carrier frequency. So they will allow the carrier signals, and those will be propagating throughout these lines over here, power lines only. Now they will come over here, and at this point we have a parallel RC circuit here. Now this parallel RC circuit will offer high impedance to this carrier frequency. So what they will be doing is, they will be having a diversion over there. So all the carrier signal will be collected there itself. So all the signals are carrier signals are collected there, means so they have reached the destination over there, because these RC circuit is basically tuned to power frequency only. They will allow only the power frequency, which is 50 hertz, to pass through them, okay, to the current transformer or somewhere like that, okay. So from there you can go for the circuit breaker, like operating like that. So that is what basically happens exactly in the case of carrier signal, right? Now see, what are we basically offering? We are offering for the trap units. These are the trap units, right? Now these are trapping these carrier signals. So they are offering high impedance to the carrier frequency, okay. So they offer high impedance to carrier frequency signals. Option B is the correct answer, okay. Let's look at the next question, 277th question. We have two lists and we need to match these two lists, okay. First list is based upon equipment and second list is based upon the function of the equipment, okay. Circuit breaker, what is the circuit breaker doing? Generally circuit breakers are designed to protect from over current, right? So therefore option 4 would be the correct match for option A, right? Right. And then I would be having lightning arrestors. Lightning arrestors, why do we have lightning arrestors? For voltage surges, right? So lightning arrestors I would be using to protect against the light over voltage protection. By governor I can control what? I can control power, right? So more steam input means more power, right? Exciter means voltage control, right? So D is basically related to 1. So 4, 3, 2 and 1. 4, 3 and 2 and 1. Option D is the correct answer, right? Like that. So let's look at the 278th question. To prevent maloperation of differentially connected relay while energizing a transformer, the relay restraining coil is biased with which harmonic current? See, in why are we using differentially connected differential protection? To prevent, to operate, to protect it from the fault currents. But what happens is, even though there is no fault also, this differential relay is operating. Why is it operating? Is, suppose the transformer is suddenly switched on. Okay, what is happening whenever we have a transformer with suddenly switched on? We would be having inrush current flowing into the transformer, right? Not only the supply current, but also the inrush current will be there. Now that inrush current, right? Now that inrush current is very higher, right? Now that inrush current is very higher, and it's not at all sinusoidal, right? And it's 8 to 10 times higher than the normal value. Now I don't want that inrush current to be present. Now that inrush current is completely comprised of, why is it not sinusoidal? Means it is higher, it is having more and more second harmonic current present in that. Okay, so if I have a a relay restraining coil RRC in the differential protection scheme, such that if I bias that relay restraining coil with second harmonic current, now I can ignore the inrush current from the protection scheme, because when I bias the relay restraining coil with the second harmonic current, whenever the inrush current is appearing in the input terminal of the transformer protection system, you can say what is happening is, these second harmonic currents are ignored by the protection system, differential protection system. Okay, they will consider them as a normal currents as well. Okay, now I can prevent the maloperation of the differential protection system, right? So therefore I have to bias with whatever the harmonic currents the inrush currents are having. Okay, so that is second harmonic current. Option A is the correct answer. Now let's look at the 279th question. We have a question from Power Economics. I have made a course on Power Economics on at Unacademy free platform only. Do check it out. It will be completely useful for you. Okay, power generation economics. I have made a course on Unacademy. Okay, do check it out on Unacademy. Free platform only. Look at the question here. Incremental cost of two generating units are given. For generating one, incremental cost is given. For the second generating unit, incremental cost is given. Okay. Now PG1 and PG2 are the real power generated by the units. Okay. Now the economic allocation for a total load of 250 megawatts, demand power is given 250 megawatts right now here. Right. Now we need to neglect the transmission losses. Okay, neglecting the transmission loss, what do we have the power generation distribution level? How do we allocate this? Okay, how do we allocate the power distribution economically? So economic allocation means optimal distribution, right? Optimum allocation means nothing but economic allocation, right? For optimum allocation, first of all, what is the primary condition? To supply 250 megawatts, some must be 250, okay, but the thing here is, how are we giving 250? Whether we are dividing them equally, or depending upon the incremental fuel cost characteristics, how? Depending upon IC1 and IC2, we must divide these, we must give the load share, okay. How is that done? To maintain economic allocation, the first thing is incremental cost must be equal, right? So IC1 must be equals to IC2, right? That is the important thing. So IC1 must be equals to IC2. Now from that I can clearly say 25 plus 0.2 Pg1, let's say that, let's write like this, okay, is equals to 32 plus 0.2 Pg1 Pg2, right? Now from this I can simplify this equation where Pg 0.2 Pg minus 0.2 Pg2 is equals to minus 7, but Pg1 plus Pg2 must be equals to how much? The demand one, which is nothing but 250, right? So from this I can conclude that from these two equations I can even write something like this. How can I write it? Like I can make it as 2 Pg1 plus 2 Pg2 is equals to 500, right? 250 into 2 means 500, right? So let's make it like that. Right? And if I take it over here, I'll have 2 Pg1 minus 2 Pg2 equals to minus 70. I can even write it like that also, or I can just keep it like that. So what I'll be having here is 4 Pg1 is equals to 430 at that time, or Pg1 equals to 140.25. will you have something like that? So 140 means I have written 25 from the options over here, okay, and from Pg2 I'll have 109, right? So 109 means I'll have 109.75. so I have calculated till here. From here I can say P1 will be something like 141, something like that. So that's the reason I have chosen option here. I'll take the option as the correct answer, and even it is given correct answer on the CL Wadhwa textbook as well, okay. So what did I do here? See, I have converted this equation. I have just written like 2 over here. I'll show you. I have taken something like this, right? I can even write it like this, right? So these two gets cancelled, for Pg1 will be remaining. That is what I'll have 430. So 430 megawatts means 140.25, something like that. So 140 option A is the correct answer. Let's look at 280th question. 280, they are saying synchronizing coefficient. It is basically synchronizing power coefficient. Okay, synchronizing power coefficient means basically we would be calling synchronizing power coefficient as something like this. PSY equals to dou by dou delta of power. Okay, so option B is correct answer. But what is P? Dou by dou delta of P is nothing but EV by XS sin delta, right? That means synchronizing power coefficient is dou by dou delta of EV by XS is going to be EV by XS cos delta, right? So like this I can even write that going to be, okay, EV by XS cos delta is nothing but synchronizing power coefficient. Okay, like that also you can this is also important conclusion from this here itself. Okay, so that's it. 280 questions till 280 we have seen it today. So the rest of the questions I'll be talking in the tomorrow's class. Okay, thank you guys. Thank you for participating in this live session. If you have any doubts, do let me know. Thank you.